Hello everyone, my name is Roberto and I'm an MET student here at Central Washington. As my senior project, I was in charge of the design, analysis, construction, and testing of the drivetrain and chassis portion for the RC Baja, which is in front of me. And the main goal was to have a functioning device that would be able to compete with everybody else during the Baja competition. And in order to help facilitate that, there were a few requirements that were created. For example, requirement 7, which can be seen right here, which states that the vehicle can reach a velocity of 30 miles an hour, and requirement 12, which states that the adhesive will be able to will not fail due to a force at a 2-foot drop, and requirement 13, which states that the chassis will deflect at most 0.1 inches due to the force at a 2-foot drop. Now, all of which would have some sort of analysis to go along with it. For example, in requirement 7, this one along with analysis 1, where the train value was calculated that would allow the vehicle to achieve the maximum velocity of 30 miles an hour, and this was done by taking the maximum RPM of the motor and then dividing it by the RPM of the rear axle, and was calculated out to be 11.96 to 1 and then rounded up to 12 to 1. Then as for requirements 12 and 13, which can be seen here, these went along with analysis number 3, which can be seen here, where the main focus was on calculating the load of the chassis that was going to be experiencing during the 2-foot drop test by using some kinematics, calculating the velocity and then the acceleration as it was falling, then plugging these values into the equation of force is equal to mass times acceleration to calculate the load that it would be experiencing. After that, since the weight of the chassis was not known, it was just assumed, as well as the chassis was later split in half and then joined together with an adhesive, a safety factor of 4 was applied when the deflection was being calculated, which can be seen here. It was also important to check the stress on the adhesive to make sure that it did not exceed the ultimate tensile strength of 1200 psi for the E6000 that was used. In order to do so, a stress equation, force over area, was applied to calculate a stress of 8.312 psi, which was well under the 1200 psi for the E6000 adhesive. And once all these analyses were then completed, it was possible to then move on to the construction portion of the project, where there were 4 major subassemblies: the chassis subassembly, the front and rear suspension subassemblies, and then the drivetrain subassembly. And back in the fall quarter, the intention was to have the majority, if not most of the components 3D printed. Because of this, additive manufacturing was the main form of manufacturing utilized in the form of 3D printing. And in order to help facilitate this decision, a decision matrix was used where the main factor was the ease of usability, comparing it to other forms like, say, laser cutting or a CNC machine, as well as the most cheapest and affordable option. Then another matrix was used to determine which material was going to be mainly utilized during the 3D printing process, and the major factor here was the weight of the material, since the entire purpose of using additive manufacturing was in order to help reduce the weight of the vehicle as much as possible. And so with PLA Plus as the main material, this allowed for a additive manufacturing to be utilized, as well as having a high yield strength, but also being less dense than aluminum or steel. During the manufacturing process of these components, there were some manufacturing issues that occurred. The biggest one was during the manufacturing of the rear axle, which can be seen here. During the first attempt, the tailstock was not engaged on the lathe when the axle was being manufactured, and because of this, without any support on this side, this caused the bit, when it was engaged in removing material, it would also slightly be pushing it outwards, causing it to become unconcentric. However, this was easily mitigated by engaging the tailstock, which can be seen right here during the manufacturing of the second axle. Then, during the assembly of the device, it was quite simple in that the majority of the components had some sort of mount that went along with it, and then this mount would then be fastened to the chassis using a threaded insert. The first assembly that was manufactured was the drivetrain assembly, which can be seen right here. And the reason for this was because it had a lot of small components that could be 3D printed, and it did not require a lot of time to print these components. And by doing it this way, it was possible to get any issues with manufacturing as well as assembly out of the way before any of the larger components were manufactured, in order to help reduce any issues and not increase the cost by much. After that, the chassis subassembly was then manufactured, where a lot of the components were simply the various mounts for the electronics as well as the chassis itself. But with the suspension and the drivetrain assembled on the device, it was then possible to move on to the testing portion of the project. During this phase, there were 3 major tests that were performed: a drop test, a velocity test, and a deflection test on the chassis. So the drop test was performed in order to ensure that the adhesive would not fail due to exceed the ultimate tensile strength of the material, which was requirement 12, and also ensuring that the clearance would be enough that it did not hit the ground during the drop test, which was requirement 14. However, during the tabulation of the data, there were several occasions where the displacement was 4 centimeters, which was the same as the clearance between the bottom of the chassis and the ground. And in order to mitigate this, changing the angle of the springs to further increase the clearance between the chassis, as well as adding some oil to the springs, which will help further increase the stiffness as well as further decrease the total deflection that was experienced. As for the stress that was experienced on the adhesive, a force of about 22 pounds was calculated due to the springs, while in the analysis a load of 30 pounds was used, and so the new stress of 6.234 psi was calculated, which was still far under the 1200 psi for the E6000. As for the velocity test, 2 velocity tests had to be performed, since the first velocity test was performed with a brush motor. However, the main issue here was that the maximum velocity was about 3.4 miles an hour, and it was noticed to overheat quite frequently due to the motor receiving a maximum amount of current, trying to produce the maximum amount of power to get the vehicle moving. However, this was lasted for an extended period of time, causing the motor to overheat, and it could be seen as the velocity then drastically increased from 3.4 to 1.2. However, once a brush motor was then used, a new velocity of about 13.2 miles an hour was experienced. And the major issue that I'm experiencing now is that at higher velocities of about 14 to 15 miles an hour, if the gears are not perfectly aligned, then this causes the teeth on the pinion to kind of wear out. And so to mitigate this, either purchasing a new pinion would be the next feasible option. However, to not increase the price of the project by much, another option would be to create a mold and then cast this pinion ourselves to help mitigate that. As for the deflection test, here the main focus was on ensuring that the deflection did not exceed the 0.1 inch requirement, which was requirement 13, as well as ensuring that, double checking that the adhesive did not fail again, which was requirement 12. And this time a deflection of 0.104 inches was calculated or experienced during the testing. However, the calculation was that it was going to be 0.0314 inches, and the discrepancy is mainly due to the fact that the chassis was assumed to be 100% solid when it was being analyzed back in the fall quarter. However, during the manufacturing phase, it was actually printed using 25% infill. And so taking this into account, a new deflection of 0.126 inches was calculated, which was fairly close, but there was still some discrepancy, which is due to the fact that there are a lot of holes that were drilled into the chassis for the various mounts, as well as the chassis is now 2 separate components that were later joined with an adhesive. And in order to be able to pass this 0.1 inch requirement, simply increasing the infill density from 25% to 35% would be enough to exceed the 0.1 inch requirement. Then moving on to here's a quick demo of the velocity test that was performed. So there was increments. The blue tape was placed after every 5 and then 10 increments for a total of 40 feet. And as you can see, as the speed increased, it became fairly difficult to kind of control, and the deviation increased. Then moving on to the schedule of the project. During the fall quarter, which can be seen here, the main focus was on the analysis as well as the writing of the engineering report, and as well as documentation of any designs that were being made to the various components in the form of drawings. Then in the winter quarter, which can be seen here, the main focus was on the manufacturing as well as the assembly of these various components, and during this time, issues with either components being dimensionally inaccurate were experienced, which either required some post-processing or either a complete reprint at times. Then in the spring quarter, the main purpose was to test all of these various components that were previously manufactured and then analyzed. The main issue during this time was with issues either completely failing during the testing process, as well as, however, this wasn't really an issue as it was possible to have a replacement by the next testing date, since 3D printers were readily available. Then the cost of the project was estimated to be about $500 back in the fall quarter. However, we are currently sitting at $830, and this is mainly due to the wheels that were purchased. And in order to make these wheels work, they required a specific set of knuckles, which costed $86, while the wheels just themselves were $72. And another big reason is due to all of the components that were not used in the final assembly of the device, which can be seen in figure 54 right here at a cost of $162. And so taking all of this into account, if someone were to make this device from scratch again, then the actual cost would be closer to $637. All right. Thank you everyone for listening. Are there any questions?